The following example involves mechanical energy as well as the force of friction. Now, in our earlier examples involving mechanical energy, we neglected friction. In this example, we are going to incorporate friction as we would in a real-life situation. So, let's look at the following problem. Suppose a block of mass 5 kilograms is traveling along a horizontal surface with a speed of 10 meters per second going this way as it strikes a spring with a spring constant of 1,000 Newton per meter. Now, if the spring compresses a displacement of 0.2 meters, find the force of friction between the surface and the object. So, we can solve this in two ways. We can use forces or we can use energy conservation. So, note that at this position, when our velocity of the object is 0 meters per second, there are two forces acting along the horizontal on our object. The first force is the force of the spring that points in this direction, and it's given by this vector. Likewise, there's a second force that points in the same direction. That is the frictional force. Now, we're not going to use the net forces to solve our problem. We're going to use the conservation of energy. So, the energy we begin with is equal to the energy we end with, where this is our initial system and this is our final system. So, energy initial, the energy we begin with, is equal to energy final, the energy we end up with. So, what is our initial energy? Well, notice initially our spring is not compressed, and that means our displacement is 0, so our elastic potential energy is also 0. Likewise, since initially our block did not yet move, that means that there is no force of friction acting on our object. Likewise, since our object is a distance h equals 0 above the ground, that means our gravitational potential is also 0. So, we should only talk about the kinetic energy because there is motion. Velocity is 10 meters per second. So initially, we only have energy due to our velocity. So that's 1/2 mv squared, kinetic energy, equals. Now, let's look at our final position. In our final system, our velocity is 0 meters per second. So that means there's no kinetic energy. So kinetic energy was transformed into some other form of energy. So now notice our spring is in fact compressed, and that means there is some elastic potential energy, and so we write elastic potential energy. Now, there is still no gravitational potential because our height is still 0, but now our object traveled a distance of 0.2 meters, and that means the force of friction must have acted on our object, increasing the internal energy of that object. So, let's incorporate the force of friction as well. The force of friction multiplied by our x, the distance traveled, because force times distance gives you the energy. So, now we are finished with our equation. Now we basically want to plug our knowns in and then solve for the force of friction. So, what do we know? Well, we know the mass is simply 5 kilograms, so we plug in the mass. We know the initial velocity, which is simply 10 meters per second, so plug that in. We also know K, our spring constant, 1,000 Newton per meter, and we know our X, the distance our spring compressed, and the distance our block traveled in the right direction. So we plug in 0.2 and 0 and 0.2. So, 10 squared is 100 times 5. 500 divided by 2 is 250. 0.2 squared is simply 0.04 multiplied by 1,000, which is 40, divided by 2 is 20. And then we bring the 0.2 on this side after we subtract both sides by this amount. So we want to bring this on this side, and then we want to divide by 0.2 so that we are left with the force of friction on the right side and everything else on the left side, because we're solving for the force of friction. So we get 250 subtracted by 20 divided by 0.2, and that gives us 1,100 150 newtons. So this is our force of friction, which points in this direction opposite to our initial motion of that object, which also points in the same direction as the force of the spring.